Episode 5 Multithreading. Welcome back. This is the 5th episode in Compensation Behind the Scenes, a series where we go in depth on the internal workings of our multiplayer social game Compensation and talk about some related computer science along the way. In this episode, we'll be going for a basic look into multithreading and multiprocessing. Without further ado, let's begin. Disclaimer. This information has been simplified somewhat for educational purposes and therefore may not be 100% accurate. For more in-depth resources, please see the link in the description below. A process is a container for operating system information. It contains a list of threads, which we'll go into in a moment. It also contains information like memory usage, permissions, and in-use file handles. A thread can be considered like a single person. Each thread has a list of instructions it should execute, and performs all of these in order as you would expect from any program. However, threads can be run in parallel on multi-core CPUs. In the event, there are more software threads, those allocated by the OS, than hardware threads, those actually run in parallel by the hardware. Operating systems typically implement a piece of the kernel called a scheduler, which essentially has the job of switching between threads extremely fast to give the illusion of more parallel threads. A kernel scheduler is a piece of software within the operating system kernel, which has the task of arranging all running processes and threads into a fairly ideal execution path for the CPU to follow. It does this by forcefully interrupting execution of the current program and swapping it for a different one extremely quickly. Originally, Linux used a scheduler called the O1 scheduler or constant time scheduler. This system was extremely well made as it was able to schedule all tasks in constant time, meaning processes were guaranteed to be switched in about the same amount of time every switch. It did this by using some interesting memory magic using pointers that I won't get into for time reasons. If you are interested, there will be a link to a Wikipedia article on Constant Time Scheduler and its replacement, the Completely Fair Scheduler, in the description. Moving on. Race conditions are an unfortunate side effect of parallelized programming. When you have the opportunity to write to one resource from multiple places at the same time, or even just read while writing from another thread, you have what is called a race condition. These can be ridiculously difficult to debug, since they're not guaranteed to happen every time due to scheduling differences or even just hardware variations. This is why we need to implement our next topic, memory and thread safety devices. Total thread safety eliminates a whole class of logic errors simply by giving you guarantees about what you're doing. When code is 100% thread safe, it means you don't need to worry about corrupting your memory by writing while reading, or even worse, writing while writing. This does not, however, prevent race conditions. Race conditions are a logic error, and therefore need to be resolved by the programmer writing the code, not by simply following a list of rules. However, while we're on the topic of thread and memory safety, I cannot go without mentioning Rust. Rust is an incredibly intelligent language using a system called the borrow checker to guarantee memory and thread safety. For more information about the Rust borrow checker, I've included a link in the description. Mutexes are one of the data structures we can use to help us with thread safety. If you're familiar with Rust, you can think of them like a runtime borrow checker, although I know I'm going to get torn apart for that analogy. Mutexes can only be held by one line of execution at a time until they are released. There are even structures like operating system level mutexes that can only be held by one thread in a process at a time, used for things like files. Mutexes are great for writing data, but what about reading, where you just need to control how many threads can access data at the same time? Semaphores are a way of allowing more than one owner of a piece of data without compromising thread safety. You can use them to limit the number of owners of data while still allowing for more than one. This is a more advanced structure, and the use cases are more difficult to explain. Overall, multithreading is an invaluable tool in a programmer's toolkit, especially for game developers. In our next episode, we'll discuss the applications and pitfalls of multithreading and compensation and how we went about using it in Unity. Make sure to tune in, you won't want to miss it. Thanks for watching.